Hello, my name is Ben Lampe, and I'm an applications engineer at Maxim Integrated. Today, I will demonstrate how to take accurate power supply bench measurements and how to easily compare that bench data with simulation data. I'll also demonstrate some troubleshooting tips if the bench data and simulation data aren't well correlated, and how comparing the simulation data and bench data side by side can help me detect discrepancies in the hardware and tune my simulation to better represent the physical design.
So, I've generated a power supply design in Maxim's online EESIM design tool and downloaded that design into the OASIS simulator for further verification. I've run simulations, including a Bode plot and a load step response, to check my stability and settling time. The design meets my specifications, so I can have a board fabricated.
Alright, now I have the board, but how can I be sure that this board's behavior will satisfy my requirements and there aren't layout parasitics or manufacturing defects impacting its performance? This is where I can leverage the OASIS simulator by importing my physical measurements taken in the lab and comparing those to the simulations side by side in the same plot. This increases confidence in the results and helps detect and pinpoint discrepancies. First things first, clean and accurate bench data is needed. Here are some tips on setting up those measurements.
To analyze the frequency response of my power supply's control loop, I'm going to use the Bode 100. This device works by injecting an AC signal into the feedback path, sweeping the frequency, and measuring the magnitude and phase response with respect to the driving signal. There's a lot that impacts this frequency response, so I can simplify things by breaking the feedback loop into compensator and modulator subsections. The compensator is measured from the output to the compensation pin. The modulator is measured from the compensation pin to the regular output.
This requires a few quick modifications to the board. First, an injection resistor in the feedback loop. I'm using 10 ohms to match my injection transformer. I've wired this resistor to a connector to easily inject the signal, and I've included extra test points at the feedback and compensation pins to split the loop measurements into compensator and modulator blocks. Then, it's as simple as hooking up the injection source and the probes. It's important to use a matched set of probes so they don't introduce their own gain and phase offsets.
After making the connections, I can launch the Bode 100 software and set up a gain phase measurement. The output level of the Bode analyzer will need careful tuning. A drive level too low will result in a noisy measurement, and too high and it will drive the loop into nonlinear operation. So the best drive strength varies over frequency, so I find it's best to go decade by decade, start small, and increase the strength until the noise disappears, or I see a drastic change in the response, indicating nonlinear operation. I can track the desired output level across frequency and create a profile that adjusts the signal strength over the measurement bandwidth. Once this creates a Bode plot that I'm satisfied with, I can take the data and export it to a CSV file.
Next, I'll measure the load step response of the board. For a fast slew rate, I use this FET load board soldered directly to the output to minimize series inductance. The FET gate is driven through a function generator. The voltage level sets the current, and the rise and fall time set the slew rate. The step current is measured across the series resistance in the source. I'm keeping the duty cycle low to avoid heating the FET and changing its on resistance. The sense resistor should be sized to drop about half the output voltage, so the FET isn't too sensitive to the gate voltage.
Finally, consider my test bench. I use a function generator to drive the load step through the FET board. The resistors on the FET board monitor the load current, and the scope triggers on the rising edge of that step. Output voltage is measured directly across the output capacitors, keeping the probe's ground lead as short as possible by soldering it to a test point across the capacitor. On the scope, this is an AC coupled measurement, the bandwidth limit is set to clear up noise, and averaging is on to get the average step response over several tests. After it finishes, I can export both the load step and step response as ASCII files for use in OASIS. The OASIS waveform format is ASCII data in two columns, the first for the x-axis and the second for the y-axis. The first row should be the axis names, and the columns are separated by a single space. If the data needs modification, like normalization or offsets, That can be done in Excel before copying the data into a text file to format it. Then the data can be copied and pasted directly on top of my OASIS simulations. One other modification I can make in the schematic is to replace the step load with a piecewise linear load using the data taken on the bench. That way, both the simulation and our physical board are responding to the exact same load step. When I overlay the measurement data with the simulation data, there are some clear discrepancies. To get a better idea of where these come from, it's easiest to look at the AC analysis data. If we look at the full loop response, we can see that the measurement has about twice the bandwidth that we expected from the simulation, and the phase has some deviation in the mid-range. The reason for this becomes much more clear if we take our measurement and split it into compensator and modulator subloops. If we look only at the compensator block, the measurement stays true to the simulation. However, in the power modulator stage, the pole associated with the output filter breaks much later in the measurement than in the simulation. This is because the simulation didn't account for the derating of the ceramic output capacitor due to the DC output voltage. I measured the output capacitance on the board while under bias and found that it derates significantly, which I can now account for in the simulations. Once I've adjusted the output capacitance in OASIS, the AC analysis lines up nicely, and I can expect the simulation to behave like the board. If I run a new transient and paste the bench measurement in, the step response of the model lines up precisely with the measured response, accurately predicting the maximum deviation and settling time.
Using OASIS for a side-by-side comparison, I now know that my measurements were done accurately and my simulations are doing a fantastic job of modeling my power supply's actual response. I can use the simulation to verify the design across various conditions and tolerances, and ultimately carry on testing the rest of my product with the utmost level of confidence in my power supply. Thanks for joining me in my home lab. I hope you learned a thing or two, and we'll see you next time.